Tableau 3, Part 3, Beyond Balls and Urns, Unequal Probabilities and Infinite Spaces. So, in our earlier tableau, we looked at chance in commonplace combinatorial settings where the metaphor of a ball and urn was appropriate and led to purely combinatorial ways of evaluating chance and computing probabilities. We will now want to move on to a setting where chance is at play, but outcomes are not equally likely. Let me immediately begin by giving you an example from the popular lexicon. This is in the game of craps. Now, the game of craps is played by throwing a pair of dice repeatedly and summing the face values. The question here is, what is the chance that you win on the very first throw in craps? So let's walk into the game. So if you walk into a casino and you see a game of craps going, this is roughly how you'll find it being played. The game proceeds, as I've told you, by repeated throws of a pair of dice. At each throw, you sum the face values of the dice. And depending on what the sum is, you have one of three possibilities. You either win, or you lose, or the game continues by further throws of the pair of dice. Now, we are going to look at the simplest version of the game. If in the first throw of the pair of dice, you happen to roll a 7 or an 11, then you win immediately. If you were unlucky enough to roll 2 or 3 or 12, then you lose immediately. If the sum of the face values is 4, 5, 6, 8, 9, or 10, then you continue playing by repeatedly rolling the pair of dice, summing the face values at each time, stopping at the first instant where you either replicate your original throw, 4, 5, 6, 8, 9, or 10, or you have the misfortune of throwing a 7. If you replicate your original throw on the concluding throw, you win. If you happen to throw a 7 on the concluding throw, you lose. Now, let's look at the first part of the game, where you look at one throw and you ask, what is the chance I win? What is a proper model for this experiment? Now, before we launch into an analysis, we should come up with a way of describing mathematically what is going on. What are the outcomes of this thought experiment? Well, you realize that if you throw a pair of dice, then the smallest of the face values is 1, and therefore the sum of face values is going to have to be at least 2. On the other hand, the largest of the face values of the die is 6, and so the sum of the face values cannot exceed 12. And so it becomes apparent that in this thought experiment, for one throw of a pair of dice where you sum the face values, the outcomes are the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. What is the measure of chance we should ascribe to these basic possibilities? Now let's decompose the game down a little bit further. So the possible outcomes of the experiment as far as chance and craps is concerned are the numbers 2 through 12. But you can arrive at these numbers in a myriad of ways. Let's visually take a look at how we could do this. The result when you throw a pair of dice is going to be a pair of numbers, one for each die, die 1 and die 2. We can, as before, arrange these in a 6 by 6 grid of possibilities. Now, which of these possibilities trigger the value 2? Now, naively, we might have thought, before we did any analysis, that, well, there are 11 possibilities, 2 through 12, and they should all then be equally likely. Each should have a 1 in 11 chance of arising. But just a little thought shows that that is not very right. That our logic was missing ways of partitioning the problem, and that certain numbers have much richer partitions than others. For example, to get to a sum of 2, there's only one way of doing this. Each die will have to show a face of 1. Well, how about 3? Now, at this case, you have 2 possibilities. The first die could show 2, and the second die could show 1, or 1 and 2. What about 4? Now there are 3 possibilities, and now you're beginning to see a pattern. It's going across a diagonal on your 2-dimensional grid. 5 has got 4 possibilities. 6 has got 5 possibilities. And 7 has 6 possibilities. And now we hit diminishing returns. At 8, the number of possibilities is smaller. It's 5. For 9, you have 4 possibilities. For 10, you have 3 possibilities. For 11, 2 possibilities. And finally, for 12, the only way to configure a 12 is if you roll a 6 for each of the dice. And now this immediately gives us an idea of what the natural chance mechanism that should be ascribed is. So we're beginning with a set of 11 possibilities for a chance experiment. They are arrived at by various combinations for a pair of dice. And since there is no reason to expect any one combination for the pair of dice to be any different from the others, we ascribe to all possible pair combinations the same chance of 1 in 36, and therefore a natural ascribing of chance in this experiment is to assign to 2 the chance of 1 in 36, to assign to 3 the chance of 2 in 36, to 4 the chance of 3 in 36, and so on, to 7 the chance of 6 in 36, and now the numbers start decreasing. 8 has got a chance of 5 in 36, 9 of 4 in 36, and finally 12 has a chance of 1 in 36. From a modeling point of view, this is equivalent to considering a situation where you had an 11-sided die with the numbers 2 through 12 inscribed on the various faces, but the die is loaded. 2 and 12 are unlikely to occur. They occur only 1/36 of the time. If you do the experiment 36 times by rolling this loaded die 36 times, you'd expect to see a 2 only on average about once in those 36 tries. 7 is the most heavily loaded outcome for this 11-sided die. It occurs 6 in 36 times, or once every 6 rolls. We now have an understanding of a chance experiment with a finite number of outcomes, 11 outcomes in all, the numbers 2 through 12. But these outcomes are not equally likely, and it is clear now from the setting why they should not be equally likely. We have identified events in this setting. The event that I have succinctly labeled win, standing for the concept of winning on the first throw at craps. But this we identify very concretely by the pair of elements, the aggregate of elements 7 and 11. You win if you happen to throw a 7 or 11 on the first throw. The event lose we identify with an aggregate of 3 elements, 2, 3, or 12. And a third event, which is that you continue after the first throw on craps if you throw any one of the aggregate of 6 elements, 4, 5, 6, 8, 9, or 10. Our next step in the program is naturally enough to ask, how should we assign chance to these events? And now we're going to touch upon a central principle, not just in probability, but in all of mathematics, the hugely important principle of additivity. This principle captures the idea that is implicit, that the whole is always the sum of its parts. At its heart, additivity is a guiding principle which suggests that if a problem is partitioned into pieces, we can assemble the whole by simply putting together and adding up the individual pieces. sounds banal, sounds trite. And you look at me and say, like, duh. But this principle, you will say, is incredibly nuanced, incredibly subtle, and the engine which fuels some of the most delicate and sophisticated analyses in the subject. Now, let's put this understanding of additivity to work in this very simple setting. To win on the first throw at craps, the event I have succinctly just called win, means that I throw a 7 or an 11. In other words, you decompose or partition the idea, the event of a win, into either a 7 being thrown or an 11 being thrown. And therefore, the principle of additivity says, to the event called win, I ascribe a chance, in notation, P of win, which is obtained by adding up the probabilities of throwing a 7 or an 11. Very simple, very deep, and here's the guiding principle of additivity. So the probability, we see, by just looking at our table, the probability of winning on the first throw at craps is 2 in 9. Well, what about the probability of losing on the first throw of craps? Appealing to additivity again, we look at the event lose as corresponding to throwing a 2 or a 3 or a 12. The probability of losing, therefore, is a sum of the chance probabilities for each of these objects. And looking at our table again, we see that it evaluates to 1 in 9. Pause the lecture for a moment while you work through and verify this simple calculation. And now we find that the chance of winning on the first throw in craps is twice that of losing on the first throw in craps. Should you hasten to the casino and start playing the game? Not so hasty. We've forgotten a third eventuality. The possibility that the game does not conclude on the first throw, but continues. Let us ask now, what is the chance that you will continue playing craps after the first throw? Well, the event continue is identified with an aggregate of 6 elements. 4, 5, 6, 8, 9, or 10. The principle of additivity tells us we compute the probability of continuing by simply adding up the individual probabilities. And a quick look at our table tells us the chance of continuing in craps is 6 in 9, or 2 in 3. There's a 2/3 chance that the game of craps will not conclude on the first throw. This is the lion's share of the possibility. And so the next question would be, of course, well, what if the game continues? Now what is my chance of winning? Well, that story will have to wait until we develop a little more machinery. So thus far, we have now looked at our combinatorial setting, where we have a chance experiment with a finite number of outcomes, each equally likely, and now moved into a setting where the outcomes are still finite, but the die is loaded. The coin is not fair. The individual outcomes do not have an equal chance. The next step in the program is to go beyond finite outcomes to settings where the outcomes are, at least in principle, infinite. Now, the listener might well ask, well, why should I care? Isn't any real experiment explicitly finite? Yes, but there is a virtue in considering settings where the experiment can, as a model, in principle, continue indefinitely. Let me give you a concrete illustration. For example, in evaluations of risk, actuaries prepare actuarial tables which provide elements where you talk about life expectancy and the chance of a life expectancy. But these actuarial tables carry on much beyond real life expectancies. Now, why should we do this? Well, there are two reasons. One, you would say, it is artificial to put a limit on human life and saying, well, you can't live past 101, for example. That is artificial, and clearly there will be occasional, albeit rare, examples where that number turns out to be insufficient. So it is artificial to put constraints on the number. You might as well imagine a setting where things are unbounded. A second virtue in allowing the numbers to become unbounded, in principle allowing infinite or unbounded life, is that by not putting an artificial boundary around a problem, constraining it, the analysis becomes smooth and simple. We are not put into a corset by boundaries which are artificial in nature and don't inform us about the essential nature of the problem. So in such settings, we'll think of a sanitized model where we can imagine conceptually an experiment which goes on forever. This is an example of a thought experiment, a Gedanken Experiment, an experiment which can be conceived of, but which might never actually be done. This is in exactly the same spirit as in Euclidean geometry, where we take our understanding of things like lines by taking foot rules or edges of buildings or beams of light, and we axiomatize it, we abstract it, and come up with a Euclidean idea of a line being an object which has got length without breadth. But that's absurd, isn't it? What is an object which has length without breadth? Because there's no physical object which has got length without breadth. But nonetheless, this abstraction of an essential idea proves to be enormously powerful. It is in the same spirit that we consider experiments which have an infinite range of possible outcomes. And as we shall see, for many deep applications, important practical applications, this kind of modeling allows us to get to the heart of the matter. So, are there experiments we can conceive of which are not hideously complicated, which could, in principle, have an unlimited number of outcomes? Let's go back inevitably to the toss of a coin.